students, today we are going to learn about two important concepts in linear algebra called rank of a linear transformation and its kernel. We know that many branches of mathematics are concerned with studying functions with particular properties. In linear algebra, a transformation between two vector spaces is a rule that assigns a vector in one space to a vector in other space. Linear transformations are transformations that satisfy a particular property around vector addition and scalar multiplication. In fact, a linear transformation is a function from one vector space to another that preserves the operations of addition and scalar multiplication. What do you mean by that? Under a linear transformation, the image of a linear combination of vectors is the linear combination of the images of the vectors having the same coefficients. In the previous lesson, we have seen that T of A1 alpha 1 plus A2 alpha 2 plus and so on plus A n alpha n equal to A1 into T of alpha 1 plus A2 into T of alpha 2 etc. A n into T of alpha n. So, that is about linear transformation. As we know, in the last session also we have discussed the basic concepts just like a glance. What is a vector space? A vector space or a linear space is the set of vectors, or a set V over the field F is said to be a vector space if there is an internal composition in V called addition of vectors with respect to which V is a vectors, with respect to which V is an abelian group, and V is closed with respect to scalar multiplication. That is, A belongs to F, alpha belongs to V implies A alpha belongs to V. And also the scalar multiplication and vector addition together satisfy the properties like A into alpha plus beta is equal to A alpha plus A beta for alpha belongs to for A in F. For A in F, alpha comma beta in V, A into alpha plus beta is equal to A alpha plus A beta. And also you have for A and B belongs to F, AB into alpha equal to A into B alpha. In particular, 1 into alpha is alpha. Here 1 is the multiplicative identity. So, coming to vector spaces, you have one more subset. What about the subsets of vector spaces? What about the subsets of vector spaces? All subsets are vector spaces or not? Okay. So, if a set A has n elements, it will have 2 power n subsets. But here V, if you take V is any non-empty set, now we check whether all the subsets of V are subspaces or not. Before that, we will define a vector subspace. What is a vector subspace? A non-empty subset W is said to be a subspace of V if W itself is a vector space. That means a subset of V and which satisfies all the properties of vector spaces is called a vector subspace, or W is said to be a subspace of vector space V if alpha comma beta belongs to W and A comma B belongs to F. One must have A alpha plus B beta belongs to W. So, actually this is the necessary and sufficient condition for a non-empty subset W to be a subspace of V. Otherwise, for every subset we can't check all the properties of vector spaces. So, we will make use of the theorem that W is a subspace of V if and only if A alpha plus B beta belongs to W for every A comma B belongs to F and alpha beta belongs to W. Just let us see one example for this vector space, how a vector subspace will be. Suppose A1, A2, A3 are fixed elements of a field F and W set is the set of all triads or set of all vectors of the form x1, x2, x3 belongs to x1, x2, x3, where these are elements of field F such that a1 x1 plus a2 x2 plus a3 x3 is 0. This is subspace of V3F. So, what we will do now? We will take alpha and beta in W and fixed elements of field F a1, a2, a3, and we prove that a alpha plus b beta belongs to W. That means, see here, you have alpha is an ordered triad x1, x2, x3, and beta is ordered triad y1, y2, y3. Then x1, x2, x3, y1, y2, y3, these are all elements of F such that a1 x1 plus a2 x2 plus a3 x3 is 0 and a1 y1 plus a2 y2 plus a3 y3 is 0. So, if a comma b belongs to F, then what is a alpha plus b beta? This is nothing but ax1 plus by1 comma ax2 plus by2 comma ax3 plus by3. Students, always whenever you listen a lesson on YouTube, be ready with the pen and paper so that you can calculate things like a alpha plus b beta. Now consider a1 into here you have ax1 ax1 plus by1, ax2 plus by2 comma ax3 plus by3. It is nothing but a alpha plus b beta. Substitute here a1 x1 plus a2 x2 plus a3 x3, or if you substitute you get a into a1 x1 plus a2 x2 plus a3 x3 plus b into a1 y1 plus a2 y2 plus a3 y3, which is nothing but a into 0 plus b into 0, that is 0. That means whenever you have a1 x1 plus a2 x2 plus a3 x3 is 0, then you have x1 x2 x3 is in W. So, here also you have a alpha plus b beta is 0. So, you will have a alpha plus b beta belongs to W. What is the conclusion now? W is a subspace of V. Now, we discussed the linear span, linear combination in the earlier lessons also. Just let us give a glance. What do you mean by linear combination? A set S, suppose consider a set S containing the vectors alpha 1, alpha 2, etc., alpha n, and alpha is any vector in a vector space V. Then if alpha can be expressed as a1 alpha 1 plus a2 alpha 2, so on an alpha n, that is one vector can be expressed as the addition of vectors with help of scalar multiplication, then it is called linear combination. Linear combination means every vector alpha can be expressed as a1 alpha 1 plus a2 alpha 2 plus so on an alpha n. If you consider set of all these linear combinations of vectors, then it is called linear span of S, and this linear span contains only the linear combination of elements of S, and it is the smallest subspace. No need to verify, because when if you take alpha comma beta belongs to L of S, then a alpha plus b beta is also belongs to L of S. Why? Because when alpha is a linear combination of elements of S and beta is a linear combination of elements of S, then a alpha plus b beta is also a linear combination of elements of S. Therefore, L of S is the subspace, and it is also a smallest subspace, that is L of S is contained in every other subspace. One more important concept to find the dimension of range of T and null space of T, we need the linear dependence and independence of vectors. When do you say that a set of vectors alpha 1, alpha 2, etc., alpha n are linearly dependent? If there exists scalars a1, a2, etc., an, not all of them 0, but a1 alpha 1 plus a2 alpha 2 plus and so on plus an alpha n equal to 0. In that case, we say that set of vectors is linearly dependent. But whenever a1 alpha 1 plus a2 alpha 2 plus and so on, an alpha n equal to 0 vector implies a1 equal to 0, a2 equal to 0, etc. an equal to 0, we say that the set of vectors alpha 1, alpha 2, etc. alpha n are linearly independent. See, at the last class, we have discussed the dimension of a vector space. When do you say that a set of vectors S is a basis for V? If S contains linearly independent vectors and S spans V, that means each vector in V is a linear combination of finite number of elements of S. So, the vector space VF is said to be finite dimensional if there exists a finite subset S of V such that L of S equal to V. The number of elements in the basis is called dimension of a vector space. Students, whenever you learn theorems in a linear algebra, just go through all these concepts. First, focus on what is a vector space. If at all vector space has subsets, all of them are subspaces, or when these subsets are subspaces, and you have an idea of linear combination of elements and linear span and finite dimensional vector space. When do you say that V is a finite dimensional vector space? If L of S equal to V, that means it has a finite subset that contains linearly independent vectors which spans V. Now, in the previous lesson, we have seen the properties of linear transformations, their properties and the existence of a linear transformation. Now, I am going to find range of linear transformation and kernel, which is also known as null space of a linear combination. We know that a vector, suppose if UF and VF are two vector spaces over the same field F, then what is a linear transformation? If T of A alpha plus B beta is equal to A into T of alpha plus B into T of beta, where A and B are elements in the field and alpha beta are vectors in V. And what is a linear operator? A linear transformation T from V to V such that T of A alpha plus B beta is equal to A into T of alpha plus B into T of beta is called a linear operator. Now, coming to range of linear transformation. If U and V are any two vector spaces and T is a linear transformation from U into V, then the range of T is the set of all images beta, set of all images of elements in the vector space U, which we will write it as range of T as T of alpha belongs to V such that alpha belongs to U. That means, see here, when you are saying that T is a function from U to V, then the image set T of U is a subset of V. Here, range set of T is a subset of V and at the same time it is a subspace of V. That means, range set of T is a vector space itself. That means, it is a subspace of V. So, we prove this. How you prove? Suppose you have to prove that our range of T is subspace. For that, take two elements in range of T and two elements in the field. Let beta 1, beta 2 belongs to range of T. Then, by definition of the function, there exists pre-images alpha 1, alpha 2 in U such that T of alpha 1 equal to beta 1 and T of alpha 2 equal to beta 2. Let A comma B belongs to F, then you have, what do you mean by A beta 1 plus B beta 1? That is A into T of alpha plus B into T of beta. You apply linear transformation, it is nothing but T of A alpha 1 plus B alpha 2 which belongs to range of T. because A alpha 1 plus B alpha 2 belongs to U. And why A alpha 1 plus B alpha 2 belongs to U? U is a vector space. Being a vector space, it is closed with respect to vector addition and scalar multiplication. So, range of T is a subspace of V. On the other hand, let us define null space. What do you mean by null space? In abstract algebra group theory, we have seen kernel of homomorphism. What is the kernel of homomorphism? If G and G dash are any two groups, kernel of homomorphism is a set of those elements which are mapped onto the identity element of G dash. Here also linear transformation is also like a homomorphism, vector space homomorphism. This is, so we can talk about kernel, or we call it as a null space. Why it is not null space? Null space is denoted by n of t, which contains elements of the form alpha belongs to U such that t of alpha equal to 0. That is the set of all those elements alpha belongs to U that are mapped onto 0 vector of V. I told you, whenever you are writing t of 0 equal to 0, 0 on the left side is 0 vector of U and right hand side is 0 vector of V. Now, clearly, because see here how you define null space. Null space is a set of all alpha belongs to U such that t of alpha is 0. By definition, it is clear that null space is a subspace of U. And also you have t of 0 is 0. From the properties of linear transformations, we proved that to t of 0 equal to 0. That means null space is a non-empty subset of U. Non-empty subset of U. Now we prove that null space is a subspace. When it will become a subspace, take two elements from null space. That is, let alpha 1 comma alpha 2 belongs to null space of T. Then T of alpha 1 is 0, T of alpha 2 is 0. Now A comma B belongs to F. Then A alpha 1 plus B alpha 2 belongs to U, and T of A alpha 1 plus B alpha 2 equal to A into T of alpha 1 plus B into T of alpha 2, which will give you 0. That means you have, whenever T of alpha 1 0 and T of alpha 2 is 0, T of A alpha 1 plus B alpha 2 is also 0. What do you mean by this? You have, for every A comma B belongs to F and alpha 1 alpha 2 belongs to null space of T, you have A alpha 1 plus B alpha 2 belongs to null space of T, which shows that null space is a subspace of V. Next, we are going to prove one very important theorem in linear algebra regarding linear transformations. Suppose you are saying that T is a linear transformation from a vector space U to a vector space V, then what about the rank and nullity of a linear transformation? Because range is a vector space and null space is a vector space, both will have their dimensions. So, we call the dimension of range of T as rank of T, and the dimension of null space as nullity of T, and easily we can prove that rank T plus nullity T is nothing but dimension of the domain vector space U. So, we denote rank of T by row of T, which is nothing but dimension of range of T, and nullity of T is denoted by nu of T, which is dimension of null space of T. Now, we prove rank and nullity theorem. Suppose T is a linear transformation from a finite dimensional vector space U into a vector space V. Then rank and nullity theorem says that rank T plus nullity T is equal to dimension of U, or row of T plus nu of T is n. Students, be ready with a pen and paper. just do along with me. I will be explaining. What do you mean by a finite dimensional vector space? Since U is finite dimensional vector space, you have null space, because null space is a subspace of U. Since U is finite dimensional, its null space is also finite dimensional. Let dimension of T is equal to K. That means its basis alpha 1, alpha 2, etc., alpha k is a basis for n. That means basis of null space contains k vectors, and this alpha 1, alpha 2, etc., alpha k is a basis. You are saying means it is a linearly independent subset of U. It is a linearly independent subset of U, and we know from vector spaces that every linearly independent set is either a basis or can be extended to form a basis for U. Here you have dimension of null space is k, and you have n elements in U. Therefore, you can form or you can extend the basis of null space to basis of U. That means let alpha 1, alpha 2, etc., alpha k plus 1 and so on, alpha n be a basis of U. Because dimension of U is n, its basis will containing n elements. So, whenever alpha 1, alpha 2, etc., alpha n are in U, then their T images, T of alpha 1, T of alpha 2, etc., T of alpha k, comma T of alpha k plus 1 and so on, T of alpha n, these are all elements in range of T. That means here at the same time you have alpha 1, alpha 2, etc., alpha k, these are elements of null space. So, all these vectors will become 0. So, here we claim that T of alpha k plus 1, T of alpha k plus 2, etc., T of alpha n is a basis for the range of T. This is what we are going to prove. So, if you want to prove these vectors form a basis of T, first we prove that these vectors will span the range of T and they are linearly independent. So, that range of T contains n minus, dimension of range of T contains n minus k vectors. Now, so first we prove that T of alpha k plus 1, T of alpha k plus 2 and so on, T of alpha n span the range of T. What do you mean by that? You take one vector beta belongs to range of T, then there exists alpha belongs to U such that T of alpha equal to beta. So, what is alpha belongs to U? What do you mean by alpha belongs to U? Alpha is a linear combination of its basis vectors. That means alpha is a1 alpha 1 plus a2 alpha 2 plus and so on plus ak alpha k and so on an alpha n. Take T on both sides and apply the linearity property of T. That means you have T of alpha is nothing but a1 into T of alpha 1 and a2 into T of alpha 2 plus and so on plus ak into T of alpha k plus ak plus 1 T of alpha k plus 1 and so on an into T of alpha n. Students, here alpha 1, alpha 2, etc., alpha k are basis vectors of null space. Therefore, their T image is 0. So, you have your T of alpha, any vector in range of T is linear combination of T of alpha k plus 1, T of alpha k plus 2, etc., T of alpha n, which says that the vectors span the range of T. Now, we prove that the vectors are linearly independent. I told you while defining linear independent vectors. What do you mean when you say that set of vectors alpha 1, alpha 2, etc., alpha n are linearly independent? Whenever a1 alpha 1 plus a2 alpha 2 plus and so on an alpha n equal to 0 implies either a1 equal to 0, a2 equal to 0, etc., an is 0. So, Consider to prove T of alpha k plus 1, T of alpha k plus 2 etc. T of alpha n are linearly independent. Consider a relation of the form Ck plus 1 into T of alpha k plus 1 plus Ck plus 2 into T of alpha k plus 2 plus and so on Cn into T of alpha n equal to 0. Apply linearity property of T, you get T of Ck plus 1 into alpha k plus 1 plus Ck plus 2 into alpha k plus 2 plus and so on Cn alpha n is equal to 0, means you have Ck plus 1 alpha k plus 1 and so on. This belongs to, whenever T image of this element is 0, that is will be automatically in null space of T, and this vector Ck plus 1 into alpha k plus 1 plus Ck plus 2 into alpha k plus 2 plus and so on plus Cn alpha n is equal to, it can be expressed as linear combination of elements of null space, which is nothing but b1 alpha 1 plus b2 alpha 2 so on bk alpha k. Take all the vectors left hand side, you will get because alpha 1 alpha 2 etc. alpha k plus 1 comma alpha k plus 2 etc. alpha n, these are all vectors in the basis of U. So, they are linearly independent. So, the constants b1 is 0, b2 is 0 etc. Ck plus 1 0, Ck plus 2 0 etc. Cn equal to 0. So, the vectors T of alpha k plus 1 comma T of alpha k plus 2 so on T of alpha n are linearly independent. What does it mean here? T of the vectors or set of vectors T of alpha k plus 1 comma alpha k T of alpha k plus 2 etc. T of alpha n form a basis for range of T, so that dimension of range of T is n minus k. Dimension of range of T is n minus k, dimension of null space of T is n. So, what is n minus k plus k, which is n. Therefore, dimension of range of T plus dimension of null space of T is equal to dimension of U. This is called the rank and nullity theorem, which plays one important role in linear transformations. And the next one, suppose, so what are the consequences of after defining this range of T and null space of T? Suppose V is a vector space and T is a linear transformation from V into V. Then the following statements are equal, that is range set of T intersection null space of T. They do not have other common elements except 0, because both are vector subspaces. So, they will have only one element in common. So, our range of T intersection null space of T is 0, and the second one T of alpha equal to 0 implies T of alpha is 0. So, which can be proved very easily. Students, now we will find a null space for a given linear transformation. Consider a linear mapping T from V2R to V3R defined by T of AB equal to A plus B comma A minus B comma B. So, do on a paper this one. So, what is the basis for V2R? We know that 1 0 comma 0 1 is a standard basis for V2R. Now, find T of 1 0. What is T of 1 comma 0? It is T of AB is A plus B comma A minus B comma B. So, you have T of 1 0 is 1 1 0, T of 0 1 is 1 minus 1 comma 1. So, which belongs to V3R. Therefore, these vectors span range of T. In this lesson, we have learnt about range of linear transformation and null space of a linear transformations, and we proved that dimension of range of T plus dimension of null space of T is equal to dimension of U, which is called rank and nullity theorem. And also we proved that always range of a linear transformation is the subspace of V and null space is the subspace of U, where T is a linear transformation from a vector space U into a vector space V. Thank you.